Today I'm going to talk about Wormhole. This is a pub subsystem we have developed at Facebook for delivering updates to services in a reliable way. This is joint work with people from Facebook and Cornell. So I want to start by talking about the challenge of updating stale copies of data in Facebook's infrastructure. What do I mean by that? So Facebook, which is an online social network, provides many services, and one of them is the ability to search for people based on certain criteria. For example, here, I'm visiting Oakland. I want to search for my Facebook friends living in Oakland so I can possibly meet them. To do this search, it is very inefficient to go to the primary persistent data store and pull the results from there. To make this efficient, information is indexed in a secondary index called the graph search index, based on the product graph search. Because of storing this information in an extra index, it needs to be changed or updated whenever the underlying information in the persistent data store changes. So the challenge is to update stale copies of data in an index or other secondary copies of data whenever the primary copy changes, and that's the challenge I'm talking about today. To be a little bit more specific, let's say Alice is a user who moves from Oakland to Boston. Earlier, Alice was, both the MySQL and the graph search index both said she lives in Oakland. Now, the primary persistent storage, MySQL, says she lives in Boston, but not the graph search index. Now, if I search for my friends living in Oakland, one of the results will be Alice, which is clearly not correct. And that's what I mean by we need to update the graph search index to reflect the information in the primary data store. So speaking of updating the information in the graph search index, it's not just the information in the graph search index that need to be updated. We also cache data in Memcache for faster delivery to the users. We also cache in Tau, cached inside Facebook, which needs to be updated. We also cache in Newsfeed index, and there are various such applications which keep the secondary copy of the data which need to be updated every time the data changes in the underlying persistent storage. And it's not just MySQL that has the primary source of data. Sometimes it's HDFS, sometimes it's RocksDB. So any of these different data stores, when the primary copy changes, you want to change the relevant information in the applications also. But there are various challenges in doing these updates at a large scale. One of them is that there are tens of copies of these data, tens of applications that we need to update. So this has to be done efficiently. Also, there are heterogeneous data stores, as I mentioned earlier. There are MySQL, HDFS, RocksDB, and several other data stores that need to be taken care of. It's also imperative that we do this update reliably, because even a single missed update can result in permanent staleness of the cache, which leads to bad user experience. And we also have to deal with varying application speeds. Some applications are slow, some are fast, some are CPU bound, some are disk bound, so they move at different speeds. We have to be able to deal with them. Now, one of the obvious solutions you can think of to do these updates is that each application tails the updates from the database directly. And what do I mean by tailing? Tailing just means reading the updates at the end of the log, end of the transaction log. So you keep reading the logs from the data store and keep applying them to the application. That works okay if you have only a few applications. But as the number of applications grow, this doesn't scale very well, because each additional application puts a linear amount of load on the data store. And these are production databases. We cannot afford to put too much I/O load on the system. So we look for the solution in the pub sub mechanism. In the publisher subscriber system, we let the publisher in the pub sub mechanism let publisher tail the data from the MySQL or any data store you have, and then let this publisher push the updates to the subscriber, which in turn apply these updates to the applications. This easily lets us deal with tens of applications. A very simple change in perspective. Now, we still have a few other challenges to deal with, and that's why we developed Wormhole at Facebook. So let's talk about quickly what Wormhole is. Wormhole is a pub subsystem that runs on existing heterogeneous data stores. It doesn't use any brokers or additional data store on its own. Whatever is there in the infrastructure already, it works on top of that. It delivers updates reliably. That means it delivers updates to each interested application at least once and in order. And it handles varying application speeds using the idea of tailors, as I mentioned earlier. It is currently transporting over trillions of updates per day at Facebook. Speaking of what Wormhole is, let's also talk about what Wormhole is not. So Wormhole is not an exactly once delivery system. Sometimes some updates can be delivered more than once. And it is not a storage system, and it does not provide any ordering, global ordering across different data stores. Now let's talk about how Wormhole deals with the heterogeneous data stores challenge. So instead of publisher directly tailing from the data store, we notice that we can introduce another level of indirection, which is called the tailer, which reads the transaction logs from the data store, which are very specific to the data store, and then converts them into data store agnostic Wormhole updates, which are just a set of key value pairs. The tailer, HDFS tailer, can also do the same. It reads the transaction log from the HDFS and then converts them to data store agnostic Wormhole updates. The publisher doesn't get to see whether the updates are coming from MySQL or HDFS. It just sees data store agnostic Wormhole updates. Using this additional Wormhole update structure, we can deal with heterogeneous data stores very efficiently. Speaking of, to talk about reliability of the system, I need to go into a little bit more detail into the architecture and the design of the system. So we have the data store on top, which is writing these log messages in the transaction log, numbered 5, 6, 7, and 8. The publisher reads this transaction log. And it's not the publisher that reads it. As I mentioned in the last slide, is the tailer that reads this transaction log. And the tailer gives it to the publisher to be sent to the applications, which I'm showing the left, middle, and the right, the red, green, and blue applications. Now, data store writes a new transaction log, new entry to the transaction log. The tailer reads it and then sends it off to the publisher. Publisher copies it 3 ways, one for each application, and then sends it off. And the data is processed on the application side. Similarly, update number 10 is processed same way. Application number, the log number 11 is also processed the same way. Now, periodically, the publisher asks for, hey, application, are you done up to message number, let's say 10, just to make sure that the application has actually received the data. So it sends this done question mark message subscripted by done up to what number, done 10 to this application. Now, as I mentioned, some applications are slow and some are fast. Some of them have processed messages up to 10 and some have not. So in this case, let's say the red application has processed messages up to 10, so it sends a message back saying I'm done up to 10. At this point, publisher stores these application markers, like the application is done up to this point in the persistent storage. So it processes this done 10, and the application marker for the red application moves to transaction log number 10. At this point, different applications are processing data at a different pace. So the green application, maybe it has moved only up to 6, and the blue application has moved up to 8. And now, if our publisher crashes for some reason, when it comes back online again, it can recover the application starting from the application markers that are already stored in the persistent store. Now, this way, we can ensure that each piece of update is delivered to each application at least once using this idea of application markers. We achieve reliable delivery this way. Note that now some markers, some updates could be delivered to some applications more than once a year. To talk about varying application speeds, let's consider a scenario where some applications can fail. So here, the middle and the right application happen to fail. They are at application marker number 6 and 8. The data store is agnostic to this fact. It keeps writing updates to the transaction log. The tailor keeps reading them and sending it to publisher. The publisher realizes that there's only one application that is healthy now, so it only copies it one way for the red application in this case and send it off to the red application. It's processed there. Same thing with the application, same thing with the transaction log number 13 and 14. And of course, the application markers keep moving forward just for the red application. Now, at some point, these applications do come back online and they're healthy again. At this point, we need to replay some of the past data to these applications. Here we have a crucial decision to make, and this is a trade-off between I/O and latency. We can either have just one recovery tailor to start reading updates from the minimum of these two application markers starting at 7, which will replay data for both the applications. But the blue application will have to wait for the green application to catch up. Or we can have multiple recovery tailors which will read data at two different places, putting more I/O load but lower latency. In this case, let's go with one recovery tailor. It reads update number 7, gives it to the publisher. Publisher knows that it only has to go to the green application because the application marker for the blue application is ahead, and the 7 goes to the green application. Same thing happens to number 8. Number 9 is a different story though. The recovery tailor reads it, gives it to the publisher, and publisher again copies it two ways because the application marker for both the application, green and blue, are behind this log number. It's sent off to both the applications. And recovery tailor this way keeps moving. And of course, the application marker for the application, the green application, also moves forward because at some point the publisher receives the acknowledgement that the application has processed data. Now, more and more data keeps coming to the data store. The main tailor keeps reading this data, and the application marker for the red application keeps moving. Same thing with the recovery tailor. Recovery tailor keeps reading the data, and the application marker for both the green application and the blue application keeps moving forward. At this point, both the recovery tailor and the main tailor are reading the data from the same point in the transaction log. The publisher realizes this fact and gets rid of the recovery tailor, and now the main tailor is responsible for sending data to all three applications, and we are back to the good state again. Now, in a good state, and this is how we deal with the application, different application speed. So in the good state, we are reading the update just once and sending it off to the application 3 times or whatever number of applications that are there. So this is very efficient when we talk about I/O. So let me talk about that I/O efficiency using the idea of these tailors. So here's a production deployment where we have many publishers and many data stores, and we are replicating to 6 different applications. The amount of the top chart shows how much data we are sending from the publishers to the applications. It's between 10 and 20 megabytes per second over a period of 48 hours. The bottom graph shows how much data we are reading from the data store. And that's about 1/6 of how much we are sending it to the application. So we are reading about 1/6 of data that we are sending. So that shows the perfect I/O efficiency. Except in the middle of the lower graph, there is an application failure. In that case, we read a lot of data using the recovery tailors in the past. We read up to 5 times the data in the normal case, putting a lot of I/O load on the system. But we make sure that we do not make more than 3 tailors in production so as not to put too much I/O load on the system. Now, this is all good. It shows Wormhole is I/O efficient, but this doesn't come for free. There is a trade-off between I/O and latency. So here, in this experiment, that trade-off will be exemplified. So we have 20 gigabytes of data in this experiment, and we have 10 applications which are spread out across this transaction log. So what do I mean by that? So the application markers are spread out. One's application marker is really in the beginning of this log, needs to get all of the data. Application 2 needs to get the 90% of the data. Application 3 needs to get only 80%, and so on and so forth. Application 10 needs to get only the last 10% of the data. Now, we have a choice to make here. We can either have just one recovery tailor, which will read starting from the beginning to end, putting very, very low load on the data store, but then application 10 has to wait to get data and then it will have high latency. We can, on the other extreme, we can have 10 recovery tailors. Immediately, all applications will start getting data, but that will have very high I/O load. So in this graph, the leftmost dot shows we are running the experiment with just one recovery tailor. The x-axis for that is I/O load, how many times on an average we are reading the data. With one recovery tailor, we just read the data once. So the I/O load is just 1, but it has high latency. The rightmost point is 10 tailors at the very extreme. The I/O load is very high. We are reading the data 5.5 times on an average, but the latency is low. So using the idea of the tailors, we can reduce the latency of sending all data to all applications by 40%. And notice that most of this reduction comes up to 3 or 4 tailors. So in production, we run with maximum three tailors so as to get the most bang for our buck without putting too much load on the production databases. Speaking of this, the absolute latency of our system. So we have one production publisher. We sample one production publisher at random, and we sample 50,000 updates on that publisher. And we measure how long it takes for updates to travel from when they were written to the data store to the time they were delivered to the application. So end-to-end latency. And we notice that 99th percentile latency is 81 milliseconds. So that means if my friend Alice changed her city from Oakland to Boston, her friend should be able to search for her new location within 81 milliseconds of that change most of the time, 99% of the times. So what next? So we talked about tens of applications, heterogeneous data stores, reliable delivery, and varying application speed. What we have not talked about yet is what if the data store disk itself fails? So the publisher is sending data to the application and the disk fails. The publisher just cannot read the updates at all. It's just gone, the hardware failure. But we do notice that in Facebook's large infrastructure, we do have replication for the data store. So in a different data center, the copy of the data still is there. There is a publisher running there, so potentially we could send data from that peer publisher to the subscriber, but there are many challenges in doing it. One of them is the peer publisher doesn't know starting from where to send data. because the application markers were stored in the data store that failed. So we come up with the idea of global application markers, and we store these application markers in a global service, which is a Zookeeper-based service we use, so that the peer publisher can also read the application marker. Now, even if peer publisher could read these application markers, it will not be able to interpret them, what they mean. Because application markers are usually, they are file name and the offset within the file name, and they just won't make sense to the in the new data store. So we come up with the idea of data store agnostic positions, which are interpretable across different data stores. And we come up with a coordination mechanism between different publishers using the idea of ephemeral nodes in Zookeeper, so that different publishers know which one of them should be sending data and which one should back off. Using all these ideas, we are able to come up with multi-copy reliable delivery, which means we are able to reliably deliver updates to applications despite disk and hardware failures if there are multiple copies, and we are able to leverage them. Quickly, the multi-copy reliable delivery looks like we have red data store, blue data store. Application 1 wants data from the red data store and backup from the blue data store. Application 2 wants from the red data store only. Now, application 1, just when the data store fails, can start getting data from the blue data store. And then when the red data store comes back online, it switches to the red data store. But the application 2 has to wait, and there's a big burst. When the red data source comes back online, it will send a big burst, and then things come back to normal. In conclusion, I presented Wormhole, which is a scalable, published subscriber system in production at Facebook. It works with existing heterogeneous data store that we have in our infrastructure, provides at least once in-order guarantee despite failures, and it trades off latency and I/O using the idea of tailors. Thank you.
Hi, Sergio from Stanford. So in the case that the data store fails, why doesn't the publisher read directly from the replicated data store? Why do we have the publisher at the data store's data center do it and have the global state?
So the question was, when the data store disk fails, why doesn't the publisher read from the remote data store instead of a remote publisher sending data to the application? So in that case, what happens is the publisher, when read from the remote data store, this is usually a inter data center communication, and this is an inter-process communication that will be harder to do across different data centers.
So the applications are also not. Wouldn't that also be like inter data center communication with the applications and the other publishers?
In that case, the communication between the publisher and the application will be inter data center.
And that's better than the one publisher.
Turns out to be better. Yeah.
Okay. Thanks.
Hi, I'm Edward Tremmel from Cornell, and I wonder why you don't seem to use any kind of log compression or roll-up when there are application failures. It seems like if the application has failed and come back online, you can just ship it the entire current state instead of replaying the entire log, especially if it's very behind the times compared to the current state.
Okay, so the question was, why don't we, when the data store fails and we are transporting data across different data centers, why don't we do log compression why don't we batch the updates to send to application? One of the main reasons for not doing that is that many of our applications are cache invalidations and index updates, which need to be real time. So if we batch updates, then it has to wait, and there'll be staleness in the cache for a while.
I was talking about when the applications failed, not when the data disk failed. I said if you're still in the same data center, but the application failed, the application comes back online. At that point, it's already not in real time anymore. Why not just ship the application in the current state? So
we use a streaming protocol, and which is not, we could compress the data, and we currently just don't do that.
Okay.
I think that we should move on to the next talk, and we can take questions offline. So let's thank the speaker again.
Thank you.